the double slit diffraction. The diffraction grating, I'm not going to go through the derivations, but in diffraction grating, all that's happening is you have not a few slits, not like 2 slits, not 3 slits. You're going to have billions of slits on a little piece of, on a little guy there. Okay, you're going to have billions of slits. In fact, lots of times these diffraction gratings, what's going to happen here is you'll have line, slit, this sort of idea going on. Tons of them. Okay, light comes through, and they'll give you this something like this has 350 slits per millimeter. This guy has 350 slits per millimeter. The kind of way we do this lots of times is we create a mold by taking a diamond and scratching. By the way, you'd have to use a diamond. That's the only way you're going to get it sharp enough, fine enough point. Taking a diamond, scratching lines in something very, very close to each other, okay, and then pouring the plastic points back, right? So where the hot plastic seeps in to the lines, right, is where you're going to have the blockage. There's plastic there, and the in-betweens, there's no plastic that's going to end up. That'd be the peak, so to speak, right? So you'll have a blank little slit there that's very, very narrow. Now, and what happens here, with a screen, is the exact same thing you would expect. Pick the center point or wherever you want, and you get a excellent diffraction pattern. Now, the more slits you have, the better the diffraction pattern will be, right? The better resolved it will be. I'll let you think about resolution. The better resolved it will be. Now, this works the exact same way. This works the exact same way with the exact same equations as the double slit experiment. This behaves according to d sine theta equals n lambda. D sine theta equals n lambda. Same, right? Now, here's theta, right? This also has the equation, if you will, tan theta equals h over L, right? And this becomes, straightforward plug chug, except for D. The only difference between this and the double slit experiment is D. I got to figure out what the distance between the slits would be. I got to figure out what D here is going to be, and they don't tell me that right off the bat. They tell me something like there are 350 slits per millimeter. Okay, there are 350 slits per millimeter. This is the same thing as me telling you there are, let's say, 35. Let me scroll down to try to help you see what we're doing here. If I tell you there are 35 cars for every 70 meters. There are 35 cars for every 70 meters. What could you assume, how wide is each car? How much space does each car take up? 2 meters. Did everyone see that? If 35 cars fit in 70 meters, how wide or how much space must each car take up? 2 meters. How'd you get that? You took the inverse of that, right? You took the inverse. You did 70 meters, that's the total distance, divided by 35 cars. Divided by my 35 cars. Y'all get that? Yeah? So up here, I'm just going to do the same thing. D here is going to equal, millimeter means what? What's milli mean? -3. Good. 1. So I'll do 1 times 10 to the -3 divided by 350 to get D. Okay? Now, the great part about this is it allows us, and this is what you're going to do on Monday, it allows us to get the wavelength of light with insane precision. Right? light, you're looking at somewhere on the order of anywhere between 300 to 800 nanometers, somewhere in there. Okay. So for visible light, so we're talking, you're able to measure down to, with this, pretty accurately, 10 nanometers. Get the wavelength down pretty accurately within 10 nanometers. That's incredible. You can't do that with a meter stick, right? You can't do that with a meter stick. So let me set up a problem for you, like the one you'll do in lab. Okay, in fact, let's just get an entire sheet. I've got diffraction grating here that has, let's use our 350 slits per millimeter idea, okay? When light, monochromatic light is shown on the slit, and a screen is positioned 3.5 meters away, a diffraction pattern. A nice uniform diffraction pattern occurs such that the first order maxima, that's a bright spot, the first order maxima occurs, let's use 50. No, let's do 25. I feel like 25. Why not? 25 centimeters away from the central maximum. Okay. 25 centimeters. How I have it drawn up, how you're going to have it lab, we'll have it right. What is the wavelength of light? What's the wavelength of light? Okay. Now, the beauty of this experiment, you are able to measure, you're given the diffraction grating, it's already machined for you, so that it tells you on there how many slits per millimeter you have, and then the only other tool you need is a meter stick. The only other tool you need is a meter stick. Okay? I can take a meter stick and measure pretty precisely 3.5 meters, right? In fact, that's terrible precision. That's 3.5 meter sticks. I can go all the way down on the meter stick to what? Half a millimeter. Yeah, half a millimeter. Right? That's 0.0005. Right? I get pretty good precision out of that. 25 centimeters is pretty crappy. I can go all the way down to 25.05. Right? Half a millimeter. Half a millimeter here. Okay, on a meter stick. But all I have to use is a meter stick and get these distances. Allows me to solve the lambda. Now, start out with tan theta equals opposite 0.25 divided by adjacent occurring 0.35. Theta equals. Please pop that out for me. Please pop that out. I've got to hustle. I'm almost out of time. Don't leave the bell rings. I need to get you this. That's fine. Or you say 4.1 degrees approximately. I store that and use the precise number. Now, I'm going to take that and plug it into d sine theta equals n lambda. Right? D sine theta equals n lambda. The only trick here is what d is going to be. Coming back up here, this is 350 slits per millimeter. That means this will be 1 times 10 to the negative third divided by 350 sine of, you said 4.1 degrees equals, I went up to the first order maximum, 1 times lambda. That will allow you to solve the lambda. Okay? See y'all later.